Hello, welcome to the Autumn 2 Week 1 exam practice marking video. Let's get started. So, first of all, question 1. This question is about energy changes, which we can write as delta H in chemical reactions. Figure 1 shows a simple energy level diagram. So the reactants here have more energy than the products. Which arrow, A, B or C, shows the activation energy, which can be abbreviated to a capital slanted E and a subscript capital A. Now, just to remind you, activation energy is the minimum amount of energy required for particles to react. Now, just to show you here, from the reactants, you should always draw a continuing horizontal line along the page. Upwards from the line to the highest point is the activation energy. From the horizontal line to the products is the energy change. Now, if you draw downwards, this shows that the products have less energy than the reactants. Just do that again, but with this reaction profile. So we draw a horizontal line from the reactants. We draw from the horizontal line up to the highest point, which is our activation energy. And then we draw from our horizontal line to our products. Now, if you draw upwards, this shows you that the products have more energy than the reactants. So, from that, we know that the distance from this horizontal line to the highest point is the activation energy. So A is the activation energy. What type of reaction is shown by the energy level diagram in figure 1? So, reactants have more energy than products, which means that it is exothermic. And if you have a look here, reactants have more energy than products, so all of this energy has gone to the surroundings. So energy given out. And we know that when energy is given out, that is an example of an exothermic reaction. So, I will answer on the next page. It's exothermic and that is because the reactants have more energy than the products. And that tells us that some of that energy that was contained in the reactants must have been given out to the surroundings if it's not in the products. Next, for a reaction, the value of A is 1,370 kilograms and C is 3,230 kilojoules. Now, if we look on the previous page, A and B combined are equal to C. So I'm going to write that on the other page. So A plus B equals C. So here we've got A is 1,370. We don't know what B is. And it's equal to C, which is 3,230. Now, in order to get B on its own, we need to subtract 1,370 from both sides. Oh, that's the wrong number. 1,370. These two cancel each other out. So So I'm doing B equals 3,230, subtract 1,370. That means that B is equal to 1,860. I'll write it down here as well, and that is your answer. Next, a thunderstorm. During a thunderstorm, lightning strikes the Eiffel Tower. And that's a lovely image of a thunderstorm. In lightning, the temperature can reach, what is happening here, 30,000 degrees Celsius. So a huge temperature. This causes nitrogen and oxygen in the air to react, producing nitrogen oxide. This reaction has a high activation energy and is endothermic. Now, endothermic is when the energy of the products is greater than the energy of the reactants. So this sort of reaction. There's more energy in the products, so the energy must have come from the surroundings and the energy must have been taken in. Endothermic. And this equation represents this endothermic reaction, and they've given us the energy level diagram. So, all of this energy has come from the surroundings. We need to explain why this energy level diagram shows that the reaction is endothermic. So, first of all, we can see that the energy of the reactants is lower than the energy of the products. Or you could say energy of products greater than energy of reactants. So either way. What is meant by the term activation energy? Well, I've already told you it's the minimum energy required for particles to react. Next, the equation showing the structural formulae of the reactants and products is, and then they've given us a bond energy table. Use the bond energies in the table to calculate the energy change for this reaction. So first of all, I'll deal with the reactants, of which there are two. So I'll cross off that bond, which there's only one, so it's 945. This one, just one, it is 498. So in total, if I add those together, the bond energy of the reactants is 1,443. Now we'll do the same for the products. So there's one nitrogen-oxygen bond, but this number 2 in front, that tells us that there are 2 molecules of nitrogen oxide. So we must multiply this bond energy by 2 to give 1,260. And then to find out the energy change, you need to take the energy of bond breaking of the reactants and subtract it by the energy for bond making in the products. So let's substitute in what we know. So we've got 1,443, subtract 1,260, and that gives us 183, which is positive, and that's our final check, because we know that the energy changes for endothermic reactions are positive. I'm going to pause this video now, and we will answer the rest of the questions in the next video. Look for part 2 on the YouTube channel.